Today's podcast is on acids and bases, especially the strong acids and weak acids, and how to solve problems associated with each. Before we go on, you need to understand the difference between a strong acid and a weak acid. First of all, you need to know that the strong acids are the clobber snipers. They are as follows: HCl, HBr, H2SO4, HNO3, HI, and HClO4. That in order is hydrogen chloride or hydrochloric acid, hydrobromic acid, sulfuric acid, nitric acid, hydroiodic acid, and perchloric acid. You need to memorize those, because if they are not on this list, then they are weak. So for example, if I asked you about HF, you would say that this is an acid or a base or a salt. It's an acid because it begins with hydrogen. Is it on this list? Nope. So therefore it's a weak acid. It is not a strong acid. These are the strong acids. Now, what does it mean to be a strong acid? A strong acid means that if I have HCl and I have an aqueous solution in a bottle, I have no HCl floating around at all. I have all H and all Cl minus. So if you were to see an equation, you would see hydrochloric with a single arrow making hydrogen ions and chloride ions, and those are aqueous. There's absolutely no HCl floating around at all. It completely dissociates, which means it's a strong acid because I have lots of hydrogen ions floating around, and that's what makes me an acid. Now, what's a weak acid? I can have an aqueous solution of carbonic acid, but I'm going to have a double arrow because I don't have many hydrogen ions or many carbonate ions floating around, bicarbonate ions floating around. So what's true here is I have mostly this. Look at this. Mostly. It's dissolved, but it's dissolved as a blob. I have very few hydrogen ions and very few of these negative ions. Do you see any HCl floating around in here at all? Nope, because it completely dissociated. It wants to stay together when water says, no way, I'm splitting you up. This wants to stay together, and water says, well, okay, I'll let you. That means I have very few hydrogen ions, which means I'm a weaker acid, because if you don't have any hydrogen ions, then you don't have hydrogen ions floating around to make you very acidic. I'll show you this video. If you want to stop this and you want to watch it, you can, but I'm going to show you them at the end. This is a Ka chart, and if you'll notice, many of these Ka values on here, what's K mean again? It's an equilibrium constant. Okay, and if you have an equilibrium constant on here, then that means it's a ratio of your products to reactants. And if you have a small equilibrium constant, that means you have more products, more reactants, and less products. And didn't we just see that over here? Didn't we see with weak acids that you have way more reactants and less products? So that means these are going to have Ka values that are small. And that is going to make the difference in how you do problems. So you might have to look things up on a chart, but we'll go into that in a second. So if you let's look at these two problems, okay? Calculate the pH, POH, H plus, and OH minus of this hydrochloric acid. Here's a molarity, and I know this is an acid because it begins with H. Okay? Now let's look at this problem. Find the pH, and we can do the other stuff too, but we're just going to find the pH of a 1 molar HF solution. That's an acid too, isn't it? Okay, so it sure looks like we do these the same. But what about this acid here, HCl? Is it one of the clobber snipers? Is it on this list? It is. And if it's on that list, this is an easy problem. All you do is you do your equations. You plug and chug. Now, what kind of problem is this? Is this an acid? Yes. Is it on the clobber sniper list? Nope. That means it's a weak acid, and weak acids have Kas. It doesn't make it a harder problem. It just means you need to do ice first, and then plug and chug. Okay, so let's go back and do the plug and chug first. So what do I have here? I have 0.010 molar HCl. And I need to find the pH. I also need to find the hydrogen ion concentration, the POH and the OH minus. Well, what is this right here? This is a strong acid, which means I have HCl aqueous, which has a single arrow, completely dissociating into hydrogen and chloride ions. Meaning, if I have 0.010 molar of this, and I have none of it left, aren't I going to have 0.010 molar of this and 0.010 molar of chloride ions? And what's important in this? Do I care about the chloride ions? Nope. The HCl is completely gone. I don't care about the chloride ions because I don't care about them, right? So what's that mean? That means I know my concentration of my H plus ions. So don't I already know the concentration of my H plus? I'm going to write that over here. H plus is equal to 0.010 molar. Okay? Now, how do you find the pH? Well, you find the pH by plugging this, right, which is my hydrogen ion concentration, into pH equals a negative log of my hydrogen ion concentration. And if I do that, I'm going to end up with a value of 2. Now, I know that because there's a 1 here. I don't even need to pick up my calculator. And now that means 1.0 times 10 to the negative 2. If I ever have a 1, I simply look at this number, and that's my pH value. Now, the tricky part with pH is you have to keep track of significant figures. And they are different because it has to do with an abscissa and a mantissa with multiplying with exponents. If you're interested, it's in the appendix of your book. If you're not, then you have to trust me, and you have to know that the significant figures are after the decimal. Now, how many significant figures are here? Leading zeros don't count. Those numbers count right there. That's a trailing 0, and there is a decimal. So I have 2 sig figs, which means I'm going to have 2 significant figures after my decimal. So that means I need to fill in zeros for this. And that's my pH. So my pH is equal to 2.00. No units. Okay, so we found our H plus just by reading the problem. We found our pH by plugging into this equation. And how are we going to find POH? Well, I'm going to use this equation. pH plus POH is equal to 14.00. Which means if I plug my 2.0 in here and make this X, that my POH is going to be equal to 12.00, looking at significant figures, right? Okay, so I'm done with that. Now how do I find OH minus? Well, I'm going to use another equation, KW. And I know that KW is equal to my hydrogen ion concentration times my hydroxide ion concentration, and that's equal to 1.0 times 10 to the negative 14th. Now, do I know my hydrogen ion concentration? I sure do. It is 0.010 molarity times X is equal to this number. And I'm just rewriting it so you can see it. So that means if I divide both sides by 0.010 molar, this cancels. That's a 1, sorry. Bad penmanship there on the bottom of the screen. And so then what happens is my OH minus ion concentration is 1.0 times 10 to the negative 12 molarity. And that's how you solve for it. Now there is another way. I could take my POH and do an anti-log, but let's not do that. Okay? Not right now. Now, how do I do this? Calculate the pH of a 1 molar hydrofluoric acid solution. They give me a Ka, which gives me a big hint that this is a weak acid. If I didn't know it, I have to know my clobber snipers and figure out it's a weak acid. But the very first thing I need to do is I need to write a dissociation equation. My hydrofluoric acid has a double arrow. Now what's that mean? That means I mostly have this. Mostly HF. Okay? What's it dissociate into? H plus ions and fluorine ions. But how many? Not many. How come? Because it's a weak acid. Right? This small value tells me I have mostly reactant and very little product. It means it's not a very good dissociator. Remember back here? Weak acids don't dissociate. They mostly stick together. You mostly have your reactant. That means I have very little hydrogen and very little fluoride. Now, what do I know? I know for a fact that I have a 1.00 molar solution of this. I have none of this and none of this to start with, right? I just have a big blob of HF floating around. And I don't know how much H and how much F is floating around. I'm going to put in my ice box. Initial, I have down. Where's my change come from? My stoichiometry. I've got one here, and one here, correct? Okay? So keeping that in mind, I'm going to subtract 1x, because it's going away, add 1x, and add 1x, because each of those have a 1-to-1-to-1 relationship. Which leaves me with 1 minus x molarity for my HF, an x molarity for my H plus, and an x molarity for my fluoride. Now what am I trying to find? Oh, the pH. So that means I need to do a Ka equation. And I'm going to go ahead and write that here. And what is my Ka? It's my products over my reactants. And I'm going to go ahead and plug in my values. X, X, and 1.00 minus X. And that is all equal to a value. And they give me that value. They give me the Ka. It is 7.2 times 10 to the minus fourth. And I think you can see as you're doing these problems that you need to leave room to write. Okay? So, which I don't have much room on the screen. So you need to think about this, and we're going to be smart about this, right? We said that I have mostly HF and very little H plus and very little F. That means I'm mostly going to have this 1 molar, and very little X is going away. So this X right here, I'm going to ignore. So I'm going to write ignore because small. Right, that X is very small. I'll prove it to you in a minute, okay, when we're done with this problem. But I'm going to ignore that. That's going to make my math a lot easier. That means that that X isn't there. What's true? That means that I have X squared is equal to 7.2 times 10 to the negative fourth divided by 1. Right, when I solve my math? So it means I take the square root of this to get X, don't I? And if I do that, I come out that X is equal to 2.7 times 10 to the minus 2, and it's a molarity. That's what my X is equal to. And that's nice because that tells me that that's my hydrogen ion concentration. Now, why do I need to know that? Because what am I trying to find here? Oh yeah, I'm trying to find the pH, which means I need to plug this back in to my pH equation, which is pH equals negative log of my hydrogen ion concentration. So if I plug in that 2.7 times 10 to the minus 2, what do I get? Negative log of 2.7 times 10 to the negative 2. Ah, I keep hitting the wrong button today. And I get 1.5686. Now, how many significant figures do we have? We have 2 here, and we have 3 here. I'm limited by my smallest number, which is 2. And pH, the significant figures are after the decimal place. So I've got to look at that 1.56 and say, hey, what's the 8 do to that 6? It rounds it up. So my pH is 1.57. Is that an acid or a base? It's an acid. Why? Because it's below a pH of 7. Okay? Now, I'm going to go ahead and erase this ice box, because I want to explain something to you. Some of you are saying, why can I ignore that X? Why is that possible? Well, what do we know about that Ka value? That Ka value tells me that I've got a really bad dissociator. I mostly have HF and very little H plus and very little F minus. What if we were not to ignore that X? What if we were to plug it in? Let's go ahead and do that. What do we know X is? 2.7 times 10 to the negative 2, correct? Okay. Now, I need to solve for these X's, but I'm going to go ahead and put that X in here to show you that that 1 is not changing by much. In other words, if I take 1 and I subtract this value from it, what do you get? I get 0.973. That's the value for this on the bottom. So my equation would be x, and 1.00 minus 2.7 times 10 to the minus 2, or 0.973. And that would be equal to 7.2 times 10 to the minus 4. I'm just trying to show you what value we would come up, right? Because we're trying to come up with this as our final answer. Now, if that's true, I'm going to take that 7.24, or 7.2 times 10 to the minus 4, and divide it, or excuse me, multiply it by 0.973, and then take the square root of that. And guess what I come up with? 0.02646, which is pretty close. It's 0.026, okay? Taking some rounding errors in there, that's what my answer is. Okay? Now, let's think about this for a second. If I have this value, this molarity, when do you know when you can ignore it? When do you know that X is so small you can ignore it or not? Well, there's a 5% rule, and that 5% says that whatever my H plus is, my part, over my original starting value, my whole, times 100, if I get a number that's greater than 5%, then I need to include it and do the messy math to come up with it. So let's look at our values. What do we have here? Our calculated value was 2.7 times 10 to the minus 2. What was our starting value? 1.00, and these are molarities, aren't they? Times 100. So what do you get when you take 0.027 and divide it by 1 and multiply it by 100? You get 2.7%. And 2.7% sure is way below 5%. And therefore you can ignore it. This, by the way, is called percent dissociation. How much of my original thing, my HF, dissociated? Well, how much dissociated? Only this much. So you put your part, right here, over your starting value, your whole, and multiply by 100. Let's do another one. Nicotinic acid is a weak monoprotic acid with the formula of blah. You have a 0.012 molar solution of nicotinic acid and it has a pH of 3.39 at 25 degrees Celsius. Calculate the acid ionization constant for this acid at 25 degrees Celsius. Wow, don't you feel smart? So here you go. Let's figure out what this has. What this is here. I have a nicotinic acid and it's a weak acid. Well, they're telling me it's a weak acid, but you know what, guys? I know that's a weak acid. How come? Because it's not a clobber sniper. I know the starting molarity, and I know its pH. So now it has a pH of 3.39 at 25 degrees Celsius. That's nice because things can change if I heat things up or cool things down. This is my nicotinic acid. Okay, and I'm going to go ahead and I'm going to dissociate it. Now, what really is happening, guys, is that, and they don't typically write it with acids, they write it with bases, but they don't write it with acids, is this is actually in water, right? This solution is in water. And what's happening is this is actually tossing a proton over here. And I'm forming H3O+. plus my negative ion. Okay? So when I actually write this hydrogen, right, I don't typically put water in my equations when I dissociate, but that's actually what's happening. And so what actually happens is this H plus can also be written like this. It's a hydronium ion. So that's what I've written right here. And I'm going to go ahead and I got to ask myself, is this a weak acid? Yes. Is there a Ka? No. Well, wait, what am I finding? Oh, they want me to find the Ka. Okay, well, how do we do this? Well, you know that whenever you have a weak acid, it's an ice problem. So what do you have? 0.012 molar. Okay, we're going to ignore water. It's a liquid. Look at that. We ignore it in equilibrium. This is 0 and this is 0. This is going down by x, and this is going up by x, and this is going up by x. This doesn't matter. It's not part of the equilibrium. Okay? And if this bothers you and you don't want to write H3O plus, you can go ahead and just write H plus. I'm just showing you that because sometimes it is written as a hydronium ion. It means the same thing. So what do you know now? You know that this molarity is going down. This is a value x and this is a value x. So now what's true? Well, I'm going to go ahead and write my Ka equation. My Ka equation is my hydrogen, this nonsense over here, and my nicotinic acid. And I want to find Ka. Now, that means if I don't know Ka, I have to have a way to find all the things in brackets. How do you do that? Well, we need to find these values. To do that, we need to be able to find x, don't we? Well, what is x? It's a hydrogen ion concentration. And that means I need to use this equation. pH is equal to the negative log of my hydrogen ion concentration. Well, what do we know? We know the pH. The pH is 3.39, and that's equal to the negative log of my hydrogen ion concentration, which is my x. Correct? Right here? Well, to do that, how do I solve for that? I take the anti-log, or the second log, of my negative 3.39, close your parentheses on your calculator, and you get a value of, no room to write this, I'm going to write it right here, 4.07 times 10 to the negative fourth. Now how many significant figures do I have here? 2. So that means I need to take this 4.07, I need to round it to 1. So that 4.07 becomes 4.1, and that's the molarity, and that's the molarity of my hydrogen ion concentration. So knowing that, don't I know both of these now? I do. Which means I can take 4.1 times 10 to the negative fourth times 4.1 times 10 to the negative fourth over 0.012 minus 4.0, excuse me, 4.1 times 10 to the negative fourth. And I'm going to go ahead and solve that on my calculator. And I think you'll find that if you subtract this or not, isn't that a tiny number? It's really not going to make much of a difference. As a matter of fact, when I subtract it, the answer I get for subtracting those is 0.01159. That's not that much different than 0.012. But you can go ahead and you can, solve that. And I'm letting you solve this on your calculator while I'm doing it. And for the top number here, I get sorry, 1.681 times 10 to the minus 7th. And divide that by 0.01159. And that gives me a Ka, because that's what I'm trying to find. Of 1.45 times 10 to the minus 5. Now, where are my significant figures? I have two significant figures. So it means to round this to 1.5 times 10 to the minus 5, and that is my Ka value. And there are no units because Ka doesn't have any units. And that's how you solve. Sorry, this is quick, and it's kind of all over the place on the screen, but I think you can follow. Now I'm going to go ahead and show you, and you can stop it if you want to, an animation on weak acids and bases. I'm going to talk about it a little bit. So this is water, right? And what's true about water? It's just floating around. And so what they're saying right here is that these water molecules are just going to go ahead and we're just going to call them like a blue color. So that blue background is the water molecules. Now, when acids dissociate, as you'll see here, they produce hydrogen ions and an A minus, which is the anion. Okay, but in water, what happens is these H plus ions actually come in contact with the water molecules and they form hydronium ions. So there's some hydronium ions, there's some negative ions, and there's some water molecules. So the blue background in these is the water molecules. Okay, and the H plus can also be shown, as I showed you before, as hydronium ions, but most of it's water. Now what's a strong acid? Well, what are your strong acids? Your clobber snipers, right? Hydrochloric, they list them on the screen right here. Okay, oops, I can't do that on here. Hydrochloric, hydrobromic, okay? And so what happens when it goes into water, it's going to begin to dissolve or dissociate. And look what happens. As those H plus come in contact with the water molecules, they form hydronium ions. Mostly water in the background. And if you notice, there is no HCl left. No strong acid left. No HCl, no HBr, etc. Okay? Now let's look at the weak acids. What are the weak acids? Well, they're not the clobber snipers. What happens with them? They have Kas associated with them. And what's true, when they dissociate, they don't dissociate well. A very small amount comes off and forms H plus and then anion. The H plus forms hydronium ions. And look what I have mostly floating around. Mostly my weak acid, my HF in this case, and very few H plus ions and very few negative ions. Okay? Now, these are some pretty funny songs if you want to listen to them. This is all about that base from kitchen chemistry. That's this one right here. I can't.
Because you know I'm all about the base, true acids. All about the base, true acids. All about the base, true acids. All about the base. Yeah, it's really clear. I love those hydrogen.
Okay, so there's that right there. You're going to listen to that song? There's an acid base song. It's kind of cute. And this goes into acid base theory.
Except a proton which an acid donates.
So that's kind of a cute video. And if you're going to go into health at all, this is a rap that I found from a nursing school that actually deals with acids and bases. And if you bother to watch that, I'll ask an acid-base alkalosis acidosis question on your quiz, and you can get extra credit. And there you have it. That is how you do acids and bases very quickly. I will go ahead and redo this video another time, but with all the snow, it's something and it's better than nothing.